All right, so this is going to be section 3.1, extrema on an interval. So section 3.1, extrema on an interval. And again, this is all having to do with chapter 3 now. So we've gone away from chapter 2. We will eventually revisit 2.6 to give you guys a quiz. So kind of make sure you guys go through that worksheet that we went over. Practice it, because a quiz will be coming up soon at some point during chapter 3. Okay, so just don't forget about that stuff. But sometimes people want to ask you, like on AP exams, if you can figure out whether a function is increasing or decreasing, where it's a maximum or a minimum. So that's kind of what we're going to talk about today, is like the definition of extrema. Okay, so let me give you the actual definition of it first. So definition of extrema. So it says let f be a function defined on an interval So f is a function defined on an interval. That interval is going to be called I, which contains C. Okay, and there's two parts to this. Number one, f of C is the minimum of f on I if f of C is less than or equal to f of x for all x in I. Go ahead and write that down. I'll explain those two things. The next one I'm going to write down in a bit, but let me just write them down for you guys. So number 2 says f of C is the maximum. Actually, it probably would be relative maximum, but actually, no, it would be maximum, yeah, because they're not saying anything about anything bigger. So f of C is the maximum of f on I if f of C is greater than or equal to f of x for all x in I. So go ahead and write that down. So the main things that you guys have to focus on when they're talking about like minimums and maximums, like for the minimum, okay, they talk about how f of C has to be less than or equal to f of x for all x. In other words, what this is saying is a point is a minimum if there is no other point smaller than it. Okay, which, I mean, makes sense, right? If a point is the lowest point, then it must be the minimum. That's basically all they're saying right there, okay? The point f of C is the minimum if f of C is less than or equal to f of x for all x. In other words, there is no x value that is smaller than f of C. Remember, f of C is just a y value, okay? In other words, there is nothing lower than that. Well, same applies to the maximum, okay? You'll notice they say f of C is greater than or equal to f of x for all x in I. In other words, there is no x value that is going to give it a higher y value than the c value, f of C. Okay, so f of C is the biggest of all the points, okay, the highest of all the points. So they're just talking about max and mins. Okay, this is how you can tell if a point is like that. Now, we're not going to really utilize this too much, but it is the definition of extrema. Okay, we tend to use our derivatives to find these things, and we'll figure out how we can tell whether something is a high or low point. But this is the main definition, okay? So a lot of times we'll call these extreme values. Okay, so I'm going to put that right here. These points are called either extrema or extreme values. Most people will call them extrema. It's less to say, okay? Now, if a point, let me write this out too. If a point is either the lowest or highest point on a function or point on a graph, we can use the words absolute minimum or absolute maximum. Okay, so you have to be sure that there is no other point that is bigger than it or smaller than it. And if you know for a fact that that's the case, then you can say it's an absolute minimum or absolute maximum. So to kind of give you a easy reference, think of the parabola y equals to x squared. Okay? The origin is its vertex, right? And there is no point lower than that. So then you can say that the vertex of a parabola y equals x squared would be its absolute minimum. Now, if you think about y equal to negative x squared, well, that's the same graph, it's just upside down. So the origin, the vertex, would be its absolute maximum, right? Highest point on that graph. Okay, so absolute maxes and mins are based on the picture. Now, a graph can have a lot of different types of maximums and minimums. So if I could just kind of show you this really quick. Let me say that this ends here. Let's pretend this is the graph that we have. Okay, this graph here has no absolute minimum. Okay, and the reason why it doesn't have an absolute minimum is because this right there is saying that it keeps going downwards, right? So it never stops. So this graph would have no absolute minimum. Does it have an absolute maximum? Well, if I look, there is a high point right there. That would be considered my absolute maximum. Okay, but do you see other maximum points there? Other high points? Yeah, right? So these are called relative maximums. Okay, this right here and that right here. Relative maximum says within that interval, those are high points. Okay? But the absolute maximums and minimums say within the whole interval, not just a little interval, but everywhere, it is the highest point. It is the lowest point. Okay? You can see that I have how many relative minimums? How many relative minimums do I have? Like low points, even though they're not the lowest. I have two, right? I have one right here, and I have one right there. These are called relative minimums. Now don't worry, you're not going to have to know how these graphs look in order to be able to do this. You're just going to take a derivative, and using the derivative, you're going to figure out where it's increasing and decreasing. And then based on that information, you can tell me whether it's a max or a min. It's pretty easy, actually. Okay? But you don't have to worry about doing stuff like that, okay? No maxes or mins. And remember, a graph like this, it has no absolute maximum, but it does have an absolute minimum, okay? This would have, this piece right here would be my absolute minimum. Okay, but it has no absolute maximum, right? Because you can see it's going up forever. But the vertex of that parabola would be considered my minimum. Okay? Notice this doesn't have any other relative maxes or mins either. There's no like up and down motion, nothing like that. Okay? It just goes down and then back up. So we would say it has a relative absolute minimum in this case. Okay? So a function does not need to have a max or a min. Okay, that's something you guys should remember. A function does not need to have a maximum or a minimum. Case in point, a line. Think of y equals to x. Okay, it's just a diagonal line. It goes down as far as it wants. It goes up as far as it wants. And it doesn't go up and down, right? It's just a straight line. That has no absolute maximum, no absolute minimum. Okay, so a function does not have to have one of these things. So let's go over some examples here. So example number one, I'm gonna have to draw pictures here. Okay, so you might have to kind of do the same with me. I'll kind of do it freehand. That way we're not spending too much time drawing these things out. So what can I call this? We'll say identify the extrema of the graphs. Now I'm going to draw 3 of the same graphs, okay? And when I draw 3 of the same graphs, I'm going to kind of change them just a little bit. So let's see. Part A. So here's the first one. And we're going to go with a point at -2, 2. A point at, what is this? 1, 2, 3, 4, 1, 2. So 4, 4. Yikes. We're going to do that one for A. B, I'm going to draw the same picture, okay? Same exact picture, only slight differences. And then for C, I'm going to do the same thing as well. Same picture, slight differences. All right, so for B, we'll do this. And 1, 2, 3, 4, 1, 2, 3, 4. So we're just going to put these things right here just so we can see them. So 4, 4, that'll be open there. And the last one, let me make my marks here. And as you guys are drawing it, if you want to identify the relative maxes and min, that's up to you. So I'll just give you a second here to draw those out. Notice that part C has 3 empty dots, okay? At -2, 2, at 0, 1, and at 4, 4. Give you another 20, 30 seconds, then we'll start talking about this. All right, so for part A, does this have an absolute maximum? Yeah, where is it? At 4, 4. Okay, so I'm going to put absolute max at 4, 4. Does this have an absolute minimum approximately? Where do you guys think it is? At 0, 1. Okay. So the absolute maximum we said happened over here and right about there. The minimum, right? Absolute minimum. Does it have any relative maximums or minimums like other little high points? Not really, right? That's kind of where it ends. Now, sometimes people will say, well, what about negative 2, 2? That's kind of like a high point. My response would be, how do you know? How do you know that this graph is not doing this? I just didn't draw it. Right? We don't know if it's climbing up. Or maybe it's doing this, and you would be right in saying that that would be a high point. Right? But we don't know. So, something for you guys to be aware of, okay? Relative extrema can never occur at endpoints. Put a little note for that, okay? Relative extrema cannot occur at endpoints. Now I said relative extrema. I did not say absolute. Okay? Because if something is the highest point, then so be it. It's the highest point. So it can be an absolute extrema. Okay? But it can't be relative. The reason why I'm telling you it can't be relative, and right now we'll figure it out a little bit later, but in order for something to be relative extrema, it must show that it was either increasing and then decreasing after the point, or decreasing and then increasing. You have to be able to show that the graph was going up and down or down then up at that point. But if it's at the end of the graph, how are you going to tell me what happens to the left of the point negative 2, 2 when there's no data? Right? You can't tell me on the left side it was going up or on the left side it was going down. Like, we don't know. I could tell you that after the point negative 2, 2, the graph is decreasing. I could tell you that. Okay? But I can't tell you what happens before. So that's why relative extrema cannot occur there. Absolute extrema does not have to be proven to be going up and then down or down then up after the point. It just has to be the highest point. Right? So if you visually can tell there is no point bigger than that, or there is no point lower than that, then it must be the absolute. Now, you don't actually have to see it. You can actually do it mathematically, and we'll get into that. But yeah, what about part B? Does it have an absolute extrema? Or absolute maximum? Is there a highest point that you can see? Nobody wants to respond? Well, give me a guess. Yes or no? You got 50-50 chance. At 4, 4? Now notice there is no point 4, 4 though. Right? So you might say, oh, well, the point right before 4, 4. But then I'm going to say, well, what's that point? Right? Yeah, it's something that for us, we can't figure out, right? Since there's no point there, we're just going to say does not exist. What about an absolute minimum? Where would you say that is? At 0, 1. All right. What about absolute max for C? I'm just writing this out. What did you guys say? DNE. What about absolute minimum? Also does not exist, okay? Because it's discontinuous, okay? When there's discontinuity, you can't say the point is highest or lowest where it's discontinuous. Doesn't make sense. Now, if you notice how we had absolute maximums and minimums right here, right? So when an endpoint is considered an extrema, we call it an endpoint extrema. I know it's like totally crazy, right? But if it happens at an endpoint, if the extrema occurs at an endpoint, we call it endpoint extrema. Okay, so let me write that down. If an endpoint becomes an extrema, then we call it an endpoint extrema. So it's not that hard of a word to remember. Like, where did it happen? At the endpoint. So then it must be an endpoint extrema. All right. Now there is a theorem that you guys have to know, and not that you have to know it by memory, and this will make total sense, but it's theorem 3.1. It's called the extreme value theorem. Okay, and it says if f is continuous on a closed interval, and that's actually the key to this whole thing. I'll highlight it here for us. So if it's continuous on a closed interval, so if f is continuous on a closed interval, and we're going to call it a to b, then f has both a maximum and a minimum. Now it can be an absolute maximum, it can be an absolute minimum, or maybe it's just a relative, maybe it has many relatives and some absolutes, but it'll have both of them. Okay, it has to have both of them. So to show you a very easy example, I told you that there are some graphs that don't have any, right? I told you, what if we thought about this function? And I said, look, that doesn't have any, right? But notice, this line is not drawn on a closed interval. This is drawn over all real numbers. A closed interval means that I have to do this. So now could you say that that segment has a max and a min? Yeah, could you call them absolute maximums and absolute minimums? Like, is there anything higher than the point on the right? No, right? Is there anything lower than the point on the left? So then you can say that these would be absolute maximums, absolute minimums. And furthermore, you could say that they're endpoint extrema, right? Now, it just has to be that the function is on a closed interval. So something like this. Okay. It has, well, actually, let me see. Here's a not tricky question, but let's see if anybody can answer this. Does this have endpoint extrema? No, right? Because it's not the highest or lowest at the endpoint. This has relative extrema. Here's a relative max, and here's a relative max. And then here's a relative minimum, and here's a relative minimum. But those endpoints are not maximums or minimums. It's not the highest point. It's not the lowest point. So this graph right here would have no endpoint extrema. It would have an absolute maximum right here and an absolute minimum right there. And what are the other ones called? Relative, right? Relative maximums, relative minimums. No endpoint extrema though. And again, finding this information is not that hard when you have a picture. It's a lot harder when you don't have a picture and you got to figure stuff out in a different way. Now, let me see. I don't have to go over that because I kind of just went over that. So endpoint extrema. Let me see. Give me a second. I just want to see if I have to do this today. Yeah, I think we can do this example. We should be good. Maybe tomorrow we'll do some more. Well, no, for sure tomorrow we'll do some more. But let me show you how to do this stuff here. One more example, and then we'll stop. This will be example 2. All right, so find the value of the derivative at each of the relative extrema shown. Actually, curious if I should do it this way though. Of each of the relative extrema. Okay, so we'll do it this way. I'm going to show you guys a little different way of doing this stuff. Okay, so here we go. Part A. F of x equal to x squared. We're going to start easy. Okay, and I want to show you something that actually pertains to next section, but it's just going to be a little bit easier for us to do. Okay, so find the value of the derivative at each of the relative extrema shown prior. Okay, sorry, not shown prior, just relative extrema. I'm not doing the stuff that I had in here. So here's my first function. So let's take the derivative. So the derivative f prime of x is equal to 2x. All right, great. What would be the lowest point for this? Well, we should know x squared, the lowest point is 0, 0, right? But how would we figure it out if we didn't know this? So this is what we're going to do. This is a little bit of something new. Set f prime of x equal to 0 to find... Actually, I probably shouldn't do that. I should say... I'm just going to leave it like that for now. Set f prime of x equals 0 to find the critical numbers. Critical numbers are numbers where extrema could occur. Okay, and we're going to define that next time. Okay, maybe even next section. But I'm just trying to give you a little insight as how you do it. If you didn't know what the graph looked like, how would you figure this out? And actually, the definition for critical numbers or critical points, you figure out where your derivative is 0 or undefined. Okay, so set f prime of x equal to 0 to find the critical numbers. Here I did that just 0 because there's nothing that makes that derivative undefined, right? No number that I put into 2x is going to make it undefined. So I'm just going to solve for 0. So here we go. Solving for 0. 2x equals 0. So therefore, x must be 0. Well, that was easy. So what do I do with this? I'm going to put it in green. make a sine graph. Now, I don't mean sine as in S-I-N-E, okay? I mean S-I-G-N. This is what a sine graph looks like. You're going to get f prime of x, because we're doing a sine graph for f prime of x. You're going to do a little number line, and on that number line, you're going to label your critical number. So I usually just put it in the middle. Sometimes you have many critical numbers, so just space them out. Now, you already know that if you plug in 0 into your derivative, what are you going to get? 0, right? 2 times 0 is 0. That shouldn't be surprising because we literally just solved for what makes it 0, right? But here's the question. What happens before 0 and what happens after 0? So what number is before 0? Give me an easy one. Say it. -1. Let's plug in -1 into 0. Okay? So what do I get for f prime of -1? Notice the reason why I'm plugging it into my derivative is because notice how that graph is a graph that talks about f prime of x. That's why I put f prime of x in front of it. So what's f prime of -1? -2. So look what I'm going to do. -2, or I'm just going to put negative. I could care less what the answer is. I'm just going to do that. Put a minus. Okay? All right, give me a number after 0. A 1. If you plug in a 1, what do you get? For your derivative, f prime of 1. 2. Or, remember, I could care less about the answer. It's positive. You know what that tells me? What that minus and that plus mean? That's, how do you know it's a minimum? They're both what? Well, that point is a place where stuff is happening, but that minus and plus means a lot more than just that it was a negative and a positive answer. Think of the graph. What's the graph doing as it approaches 0? It's x squared. Parabola. What's it doing as it approaches 0? It's decreasing. You see how that's a minus sign? What's it doing after 0? It increases. You see the plus sign? The plus and the minus tell you the behavior of the graph. Now, if a graph is going down and then up, then that point, 0, must be what? It must be a minimum, right? Because it's going down and then up. A lot of times this is what I'll do once I'm done doing it. I'll draw lines and I'll say, oh, that's a relative minimum. Right? That's a relative minimum. So I'm going to write this out. I kind of did a little bit extra, but I just want to give you a little heads up on that. I can say f of x has a relative minimum at x equal to 0. Now, actually, let me erase that. Let me do it the way that they want you to do in the AP. Relative minimum of something at x equal 0. And we'll talk about that right now. But go ahead and write that down. F of x has a relative minimum of something at x equal to 0. Now, they do want you to state a little bit more on the AP, but we'll get into that when we start studying for it. Okay? The reason why I left a blank is because I have to tell them what is the minimum of the function f of x at 0. So in other words, if you plug in 0 into f of x, what do you get? Say again? Someone said it? If I plug in 0 into my f of x function, what do I get? 0. So I'm just going to write 0. Now notice, this is not the answer to my question. I've kind of gone on a big old detour. The answer to my question was, or at least the question was, find the value of the derivative at each of the relative extrema. How many relative extrema did we find? 1. What's the value of the derivative at the extrema? The extrema occurred at x equal to 0. So what's f prime of 0? 0. So let me write that down. F prime of 0 equals 0. And that's the answer that they're looking for. Okay? Now, we're going to do a part B, just another kind of simple one here, I hope. But what I want you guys to understand is if you have a relative maximum or a relative minimum, the derivative at that point is always 0. Okay, why is it always 0? Well, remember, derivative means slope, right? So I think I'm just gonna leave this. I'm gonna not even call it A. We're just gonna do that. Let me show you just a quick example. So would you guys agree that the points that I'm marking would be an indicator of relative maxes and mins for the graph? Would you guys be okay with me saying that? That those are high points and low points to that graph? Now, a derivative, one of its many definitions, now we're going to say that it can give us extrema as well. But one of the definitions we were learning before was that a derivative gives us the slope of the tangent line at that point, right? So if I were to tell you to find the slope of a tangent line at those points, would you guys agree with me that the tangent line at this point would look like this at the highest point? And over here, it would look like that. And over here, it would look like this. And here, it would look like that. Would you guys be okay with me saying that? That the slope at the highest point and the lowest point would be completely flat? Right? Because it's not going up or down anymore. It's plateaued. Right? It's gone as high as it could or as low as it could, right? So it makes sense that for every single derivative at its extrema, the slope would be 0. Okay, does that make sense? The slope at every extrema, relative extrema, shall I say, is always 0. Now, why is that interesting for me? Well, look what I said over here in green. Get the derivative and set it equal to 0, because that's how you're going to find those critical numbers, right? Also when it's undefined, but we'll get to that definition later. That's, I think, in section 2. Okay? But it's important for us to understand, that's the reason why I had us do this problem, that when we found the critical point, the critical number, shall I say, 0, and we plugged it into the derivative, we got 0, that we understand that the slope is 0. F prime of 0 is 0. The slope at 0 is 0. If this had 4 other relative extrema, and I plug all those 4 numbers in, they all would equal to 0. Okay? Because of the fact that the functions themselves, the tangent lines at a high or low point, would be flat. They would be horizontal tangent lines. Okay? So we'll stop there, and then tomorrow we'll continue.